we have disks, we have galaxies. Oh, I have to do something. And I have no pointer. Okay, I just press enter.
Yeah.
Oh, there's no pointer.
Well, got it.
Sorry,
Got it.
there's no pointer.
No. Let's go. Got it. Cursor is not, is it visible? Ah, got it? No. Okay, sorry.
It's always like that.
No, got it. Okay, go. You can, sorry, Richard. Let's go back. Okay. Okay.
There was no more.
Yeah.
Yeah,
Hide.
Yes.
Okay, good.
Sure. Sorry. Let me start again. Okay. So the basic question I want to ask, a very simple question. How do mergers affect the properties of Milky Way mass galaxies? Because already at the Milky Way mass, we have a great diversity in the properties of galaxies without bulges, to galaxies which are dead, to galaxies which are forming stars, to galaxies. How do mergers contribute to this diversity? What I'm trying to do here is to do a very simple thing. In the Milky Way, thanks to Gaia, we now have a tremendous information about the past merger history of the galaxy. It's quite complicated, but I think a consensus has been reached that we have been able to identify the last massive merger of our galaxy, and that would be the Gaia and Enceladus sausage. Okay, and we have got two vital pieces of information about it. We have got its mass through its metallicity, and we have got about the approximate time it kind of hit us, and that is through the main sequence turn-off star. So we have two pieces of information. We have mass and metallicity. And we also know that this merger did something quite drastic to our galaxy, and it caused a giant burst of star formation and perhaps even thickened the disk of it. So this is what we know from our galaxy. People have gone on to understand what are the other mergers, but the other mergers are smaller, much more difficult, and we would perhaps think that the biggest merger would cause the biggest damage. So now what I want to do is to take this intuition we have learned from our own galaxy and try and understand another sample of galaxies like the Milky Way, but which are really important in the history of how we have learned galactic formation. I'm talking about the sample which is in the local volume out to 10 megaparsecs. In fact, most of the central insight which we have and have been transferred to higher redshift have been learned from these 10 or 15 Milky Way mass galaxies out to 10 megaparsecs. Talking about M31, M81, M51, M64. There's so many of these galaxies, variety of different properties. The great thing about these galaxies also we can study them not as distant points, but I can actually resolve some of their properties. We have a lot of information about from other surveys, and so we can really study these galaxies in depth. So what I want to do now, knowing the properties of these galaxies, I want to ask the same question. What is the largest merger which hit those galaxies? What is its mass? What is its metallicity? And can I then correlate the present day property of the galaxy with the mass and the merger? Okay. So we do this in two ways. Because it's in the local volume, we can actually resolve the stars of the galaxy. In their halos. Okay, we can resolve the stars, and we resolve the stars in two ways. One is we're using Hubble Space Telescope, pencil-like beams pointed just outside the galaxy, looking at its halo. And we can also do large ground-based surveys from the ground. They are much more painful, but you can survey large areas because you can have a large telescope with a large field of view. So what I'm showing you here is a ground-based survey of M31. But we can do this very fast and quite quickly these days. So with these two things, we want these two pieces of information for all these galaxies. What is its mass of the biggest thing that hit it? And when did it hit it? That's the two pieces of information. Let's keep it simple. So the mass we get very simply by observing its RGB stars in the halo. Okay. From the RGB stars, we can get a metallicity. Okay. And using a mass metallicity relationship, we can derive its mass. Okay. This is a very simple way we do this. We look at the RGB through a Hubble HST field of NGC 253. We can identify its RGB stars, and we can find its metallicity. Now I'm going to show you immediately the results. Jump into the results. Today, in the last 8 years, we have now been able to identify about 12 to about 15 of these galaxies, the metallicities and masses of their halos for about 10 or 15 of these galaxies out to 10 megaparsecs. This you can see there's a great spread. So what I'm plotting over here is on the x-axis is the mass of the total accreted mass, which we have calculated in some approximative way. Okay. And on the right, on the y-axis is the metallicity of the halo at 30 kiloparsecs above the minor axis. So it's pure halo, pure accreted. And this is what we have got so far. Okay. The Milky Way, I just want to point out, is this point over here around, just to give you a sense of comparison, about 10 raised to 9. We see that there's a great spread. There's immediately a great spread. There are some galaxies which have accreted objects or have right up to about the size of the Milky Way. You know, some things which have accreted things which are very small. And if you can imagine and use your imagination and draw a Gaussian through these points, I'm sure all of you can do that, you will see that the median would be somewhere in the middle, around this way in the middle, that most galaxies which look like the Milky Way, the average thing it would accrete in its lifetime would be something like the X, which would be, that's a kind of the first thing you think. Some things accrete things much more larger, some things accrete things much smaller, but the average Milky Way mass galaxy accretes an LMC in its lifetime. So the first thing you learn. Okay, so we've got now a mass of everything that hit it. And
just a little bit behind it. What is exactly the metallicity in the y-axis? Is the halo metallicity?
The halo stellar metallicity. Halo stellar metallicity.
Halo. So we took just about
the point far from the plane.
We point above the plane, and we measure that particular metallicity.
Use the color of the RGB.
RGB to get a measurement.
the mass.
This is a simple, galactic scenario. The more difficult thing is to get an age, okay? To get an age of a galaxy. Now, what we are really interested in is thinking that if an LMC-like galaxy is coming in, at some point it gets disrupted and stops forming stars. Okay? It stops forming stars. So if you can measure the star formation history, or better, the shutdown of star formation history in the halos of these galaxies, you have an approximate age, just like how we have done it for the Milky Way in Gaia and Ceres. Okay, so this is really expensive in M31, which is our closest neighbor, with a really expensive HST proposal. You can go down to the main sequence turnoff, the gold standard in finding star formation history. Okay, for galaxies which are much further away, like M81, you can't go so deep. Nobody will give you that time. You can go down to the red clump stars and somehow get an age. So these are two galaxies out to M81 distance, M81 and Cen, and both of them have measurements up to the red clump, and you can get an approximate age. For more distant galaxies, it's an impossible task. You can't do any sort of measurements. One way we have developed recently is to use the AGB stars, which trace intermediate age stars, in the halos of these galaxies. So what we do is a very simple thing. We look at the RGB stars and we look at the AGB stars, and we do a simple counting, a ratio between AGB to RGB. Just count the number of AGB stars, count the ratio to the RGB stars. And what we have found using models, but also using our own Milky Way dwarf ellipsoids, that there is a correlation between the ratio of AGB to RGB to the shutdown of star formation denoted as T9. It's a very simple relation, very simple. You're doing kind of like an approximative measure. You're not comparing this to main sequence turnoff. You take this with a pinch of salt. but you have an approximate age. And you can actually calculate some sort of ages for these groups. And I will show you more about this later. So this is the basic idea of how we get a mass and a time. Okay. So next, let's try and see what we can understand, how we can interpret these results. So over the last few years, a number of us have been able to develop use cosmological simulations to develop models of how to interpret these results. And I'm going to leave you with 3 results from these models. The first thing is that if you measure the mass of the stellar halo, that is kind of everything around the galaxy, you can more or less constrain the mass of the biggest object which fell in. Okay, take for example, if the mass of the halo is about the mass of an LMC, nothing bigger than the LMC could have fallen. Is this clear? So you cannot measure the mass of the biggest thing which fallen. So in fact, in the models, there is a very simple relation between the accreted mass. It's not exactly 1-to-1, but there is, and the dominant mass of the dominant progenitor which fell in. Okay, so it's majorly, most of the halo is built up by one large object. The second message you can take from the models is that the larger your stellar halo, the more probable it is built up from a large object, single large object. That most of its mass comes from a single large object. And this really is a consequence of, how would I say, the stellar mass halo mass relationship. So you know the Milky Way, if you know the stellar mass halo mass, the Milky Way is at the knee. And below the Milky Way is a very steep relationship, which means that basically if you think that things merge hierarchically, most of the mass comes from the biggest object which fell. So what I'm showing you here is the accreted mass and the fraction of the halo which is built by the largest object. And really, if you go to higher halo masses, you really are built up by one large object. I like to give the simple illustration of saying that there are not enough small dwarf galaxies in the universe from the stellar mass function to build up a halo of a large size. There are not enough galaxies. And the best way I also like to talk about this in divulgazione, I don't know what you call it in English, but it's to talk about mergers in businesses. If we had a recent failure of a big bank in Switzerland, Credit Suisse. The only thing which could save it was another big bank, not small banks. You can't put so many small banks together to save it. So you really need something big. Okay, there are not enough small galaxies to make up a thing. Simple illustration. And the last thing is that there is some sort of a hierarchical relationship between merger time, or when you fall in, and the mass when it falls in. For instance, suppose if you have a large halo, it is more probable that it was actually built very recently, because things take time to build up in the universe. It's a very simple fact. But if you have a small halo, it could be that it actually was built up very early in time and then had a quiet accretion history, like the Milky Way, something like the Milky Way, or it could also something else could fall in the meantime. So it is just 3 correlations. Okay, let's now go into specific details. I'll just try and point out a few specific examples. The first one is our nearest neighbor, M31 Andromeda galaxy. It's a galaxy we have best studied external to our galaxy, and we have known its stellar halo from the early 2000s up to 2014, when the PANDA survey was almost complete. And what was immediately striking to the people who did the PANDA survey was M31, which is the center, has a giant stellar halo, which is about the size of the Great Dipper. This is the size of the Great Dipper. And its mass is about 10.3, half the size of the Milky Way. You count all the stars around M31. Okay. For a long time, it also had a giant stream, which you can kind of squint and you can see it over there. For a long time, people thought that this halo was built up by many small objects which fell in. And we were able to show through our models that to build a halo of the size of M31, you really need to have a very large progenitor a very large progenitor, which was accreted fairly recently. This is the plot I showed you in the previous plot. Okay, and it has to be also very metal rich, naturally very metal rich. So it had to be accreted in the last 5 gigayears, and it has to be something, you know, really, really large. You cannot build a halo like the halo of M31 otherwise. We were also able to use the tremendous data which was already available in the halo of M31, especially those ages, to look at their star formation histories. And what we found was that everything which was very metal rich and which could have come from this progenitor had an approximate shutdown in star formation history about 2 billion years ago. So the three objects which are very metal rich in M31 is M32, which is the most metal rich, strangest object, higher metallicity for its mass. There is this inner spheroid, all this debris, and this giant stream, which is also very metal rich. And all three had a shutdown in star formation about 2 gigayears ago. And we then conclude that M31, okay, had this large merger, which is kind of a model. And it merged with M31 finally around 2 gigayears ago. And that M32 would have been the disruptive core of that galaxy. This was the conclusion which we reached at that time. And the size of that galaxy would be half the size of the Milky Way. Let me also quickly say that not everybody agrees with me on this topic. Some people think that M32 had another origin, they don't know what. It would be very difficult for us in our models to put two big objects falling into M31. Cosmology, what we have of cosmology, lambda CDM does not permit having two large objects falling in together. Okay, one of the things we did was we looked at we were very interested in M32. M32, if you know M32, is a very small object, extremely large surface mass density, one of the highest surface dense objects in the universe, and very high metallicity. And we kind of try to ask ourselves, okay, if you look in the local universe, what is which galaxies are of the size of this M32P, the progenitor of M32, which is half the size of the Milky Way, and which have their same central density as M32. And we came about with about 8 examples of this out to about 24 megaparsecs. And 2 of them are actually merging. So I'd like to give you this classic example of M51B merging with M51. And that one over there is M82 merging with M81. Okay, just keep this in the back of your head that there are M32P analogs in the universe. Okay. Now, what is the consequences of the merger of M31? This information we knew before we came up with our theory, but now in retrospect, we can see that the consequences of the merger paralleling the consequence of the merger in the Milky Way. There was an immense burst of star formation about 2 gigayears ago, just like happened in the Milky Way, but much more larger. And the disk of M31 heated up. And you can measure this very clearly in the dispersion in the stars of M31 compared to that of the Milky Way. Very high dispersion. This is like a heating up of that disk. There's a very clear consequence paralleling that of the Milky Way. We knew this much before we knew the story of the Milky Way. Let me now move to this next nearest galaxy we have. The next nearest galaxy is a merging triplet. M81 merging with M82 and with NGC 307. On the left, I am showing you a large field Subaru map with there are two fields of view put together of the RGB stars covering the halo. Okay, and it's using the ground-based is much more difficult than many of you will know. It's much more difficult than using HST. You have to deal with the pesky galaxies which mask as RGB stars, but you can do it using colors. And therefore, you can actually now calculate the halo of M81. Now you can see all this area around M81 is the halo of M81. It's a very small halo compared to the halo of the Milky Way. But you can see that M82 and NGC 3077 are disrupted, are actually disrupted. You can see a lot of their material is outside their tidal radius. Okay. So what Adams Messina, who led this study, tried to put this together. So if you look at the mass the accreted mass metallicity relationship, this would be the normal relation which I showed you earlier. M81 would be around here, just close to the Milky Way. But then over time, you can imagine what will happen to this triplet. Definitely, most of the material outside the tidal radiuses, outer radius, will eventually become the halo of M81. And M81 would move from here to the green zone because its halo would grow over time. But then you can even do the wild guess that perhaps even M82 will disrupt over time, actually. And also NGC3077 will disrupt over time. And you would then jump to a very high stellar halo mass. And given the metallicities of those stars, which are very metal rich, you would jump up there in the plot. So you kind of have move it into status. And therefore, we like to put together my computer doesn't agree with my theory.
Okay.
Okay. I'm just to put together a scenario which we think is very plausible. So what we like to put is like a scenario in which what M81-82 pair is actually what would happen, what happened to M31 many years ago. Okay, about 3 or 5 years. So M81 as M82 is merging with M81. You know this. The first thing you notice is that M82 lights up, in the sense of that there is a burst of star formation, intense burst of star formation in the universe. Okay. Secondly, what you would have is the disk of this galaxy would then react as you would see in M51 today. So M51 is you have a burst of star formation in disk. Okay. So M31 would be lit up like that many years ago. And finally, we hope, because of the high central density of M82, M51b, that would be the remnant, which would be M32 at the end. It's like a thick nut of a fruit. You can, with stellar stripping, you throw out the fruit, but the nut kind of remains because it's a high central density. This is kind of the image we have in our heads. And one of the amazing things about this is that it actually challenges our idea of what collisions do to the disk of galaxies. It heats them up, but doesn't really destroy them. Or does it? Now, I don't know, because I have to show you the counter example. And the counter example is Sene, which is also around the distance of M81. I'm not going to show you any plots because we have not done a lot of serious work in this, but this is the back of our heads. M81, Sene also has a very metal-rich shape, which has been measured by Marina Richkuba. And using her metallicity, we have been able to show that the mass of the thing which merged with it must be around the size of the Milky Way. Really massive object. She also, using AGB stars, has shown that the collision was about 2 to 3 gigayears. So kind of paralleling that of M31. And yet, Sene is an elliptical galaxy. The disk doesn't survive. Why does it survive in one and why does not survive in the other is an open question. It's also an open question, but the Sene was a disk galaxy to begin with. But I'm just putting the evidence in front of you as we don't know. But I'd like to show you then the work we did with the dating of the stellar halos. So I cannot show you the masses, but now if you put together the work we did on the AGB stars, you can actually then measure their masses and measure the time they were accreted by measuring the shutdown in star formation T90. And you see with all we have about 6 measurements right now, counting the Milky Way and Sene, which are done by other people. We have about, we can see a clear correlation that the biggest halos are created more recently and the smaller halos are created, they're built up much earlier in time. Okay. I would like to end up with with 2 more galaxies, M94. M94 is a galaxy which has the largest pseudo bulge in the local universe. One interesting question we can ask is now, do mergers cause bulges? That's an interesting question. Do mergers cause bulges? So we measure the halo of M94, and you actually have 2 types. It's a very tricky galaxy because it's face on. So you have to separate the disk from the halo, kind of do it through metallicity maps, and we have measured the halo. And now I'll just kind of show you the end results, okay? So again, I'm showing you this traditional plot of the metallicity versus M accreted, and M94 is way down here. Much smaller, it has a halo much smaller than the Milky Way. So definitely such a large pseudo bulge could not have been created by a merger because there's no correlation. In fact, we can do the exercise of correlating the bulge mass with the halo mass. And there is no correlation. There is no correlation at all. And this leads us to conclude that the largest merger does not correlate with the bulge mass and probably was not caused by the largest. The bulges were not caused by the largest. It was caused by something else. It was caused probably by the previous mergers or the early merger or some other process. But it's not the largest merger, the last major mergers. Okay. Finally, this is a new thing which we've been working on. This is another nearby galaxy, M64. It's called the evil eye galaxy. It's called like this because it's the closest example of a counter-rotating gas disk. So what you see, the stars rotating in one direction, and the outer part, the gas is rotating in the other direction. And this has been a puzzle for many years, and people have kind of assumed that it was caused by a merger. And we went to look because now we can measure things. So we actually measured the halo of M64, and you can see it here using 3 fields of Subaru Hypercam is an excellent instrument. And you actually can see for the first time that M64 is actually undergoing a merge. And you can actually see a tidal stream and a plume. So it's like this tells you it's a recent merger. It's a very recent merger. And if you have to measure this mass out there, you can actually measure the masses, and they're quite small, they're not very large. So we conclude that M64 accreted recently with a very gas-rich dwarf galaxy similar to the SMC. That's the kind of the mass of it. And it kind of caused this outer, we think it caused the outer counter-rotating gas disk. Okay. And finally, the last thing which I would like to leave you with, what do mergers do to galaxies in terms of their satellites? So they're going to show you 2 examples of galaxies which have had recent large mergers. And the first thing which strikes you in both of them, one is M31, one is Sene, is that both of them have a large number of streams. You can see these streamy objects. Now, if you can see a stream in a distant object, not in the Milky Way, approximately, I can assure you that that stream must be the size of the Sagittarius stream or larger for you to see it. You won't be able to see it if it's anything smaller. So this is like a large number of Sagittarius-like streams. And you would think that these are disrupted galaxies. The question arises, what do, the LMC is bringing in a large number of galaxies. What do all these past mergers do to these galaxies in terms of their satellite content? So using models now, you can actually kind of show that as you have an accretion of, so this is look back time with the number of infalling subhalos. I'm using here a dark matter only simulation for illustrative purposes, and the number of surviving halos. Okay, you can see that as there's a merger around 7 giga-years ago, 7 billion years ago, and along with it, a large number of smaller subhalos fall. Kind of, you can assume that if you do some sort of you can sort of do a semi-analytical model, you can say half of them were satellites, etc., etc. So a large number of satellites fell in with the large merger. This is what we expect from our own intuition, from the LMC, etc. So we then went to look at the data which is there in Milky Way and M31. Dan Weiss, a few years ago, published the star formation shutdown times in the satellites of M31 and the Milky Way. Okay, and the striking thing which he found was that that in the Milky Way we have 2 types of distinct types of satellites: satellites which are just quenched and satellites which quench long around the time of reionization. M31 was a very distinct example in which they had these intermediate ages. Okay. So we took the T90 data from it, and we did a kind of a kernel smoothing. And this is the kind of the result of the kernel smoothing which you have over here. You find that this kind of plot gives you the impression that in the Milky Way, satellites fell in two clumps. One around 10 gigayears ago, and one around 2 gigayears ago. The 2 gigayears ago must be the LMC. The 10 gigayears ago, we hope it's the Gaia and associated friends. You know, it could be anything. We can't say that. But the M31, there's a big bump around 6 gigayears ago, probably something even earlier. And we associate this with this large accretion, which was there 2 gigayears and finally crashed with M31. But 5 gigayears ago, when it accreted into the halo of M31. So the satellites give you the same sort of a kind of a picture which the stellar halo is giving you, which is a nice thing for a counterbalance. So they're both telling you the same story, that M31 had a large merger about 5 or 6 gigayears when it entered the virial radius. And finally, this is data which we have found, but we don't know, and it's presented to you, but we don't know what to make of it. If we calculate now the number of satellites of the galaxies which we know, okay, and if we calculate the biggest thing which fell in, now what do I mean by the biggest thing which fell in? Is that you think of the past mergers and you think of the present accretions and you choose the biggest one. So for in the Milky Way, the biggest thing which has fell in is the LMC, not Gaia. For M31, it would be its M32P, etc., etc. So this is what is there on the x-axis. And on the y-axis is the number of satellites above a certain magnitude. And we see a nice correlation. Okay, we don't know what to do with it because we don't see this in the simulations. We don't see any of the fire simulation, Auriga. None of this nice correlation works out. It also could be that we are just missing data. It is too early in the game that there could be some galaxies out here which they're not bringing in. We just don't know. And also it tells us that if a galaxy was accreted very long ago, why should it have so many satellites? They should have been disordered. I'm just going to put this out here and say, you know, we still don't know. We published this data, but we need to find more, work on more galaxies in the future. But that's it. So I'd like to conclude my talk. Am I early? No. That the first thing is that we identified the last merger of the Milky Way. We know its mass, we know its metallicity, and we know what it did to our galaxy. And now we are just trying to use that same concept and apply it to external galaxies, which have properties very different from the Milky Way. So we have identified the most dominant mergers of M31, M81, 94, M64, and Sen-A. And we are beginning to understand the effects on these galaxies. Okay, so this is, and our hope is to do all galaxies out to 10 megaparsecs, given that we get time on HST, Roman telescope, and Subaru. And what we have found is that the largest mergers contribute to the heating of the galactic disk. There's a burst of star formation. There is an accretion of smaller satellite galaxies, but we find no contribution to the building of central bulges. This is the kind of the general ideas we get from it. Thank you for attention, and I'll be open to questions.
For the very interesting talk. Questions? David?
Yeah, thank you, Richard. I think I have too many questions.
Oh, sure. Yeah.
Let me quick. So in the last plot that you show, what is the number of satellites? I see. Okay. Okay. The next question, the previous, the comparison between M31 and
sorry.
the Milky Way.
Yeah. Yes, sir.
Is there a secondary peak around 6 years ago? And if there is, could there be Sagittarius and Friends?
Could be. Could be. It could be. Well, you mean you are referring to this little thing over
Exactly,
here?
yes.
Yeah, it could be.
Okay.
But yeah, I could.
Then my last one is on M31.
Uh,
You know, I often think of globular clusters. And there was a paper, I think, in 2019 by Mackey.
yes.
So they, by using the line of sight velocities and metallicity of globular clusters, they found room for two major mergers, or two significant mergers between.
So they found two components in the globular clusters and the halo.
Yes. So could one be related to M32?
We think so, but we don't know which. That's the strange
okay,
part. We
okay.
don't know which.
But you could use the kinematic of the globular cluster and of M32 to infer which is related.
Yeah, we think it's rather complicated. We just
Okay.
don't know so much about it. So this to tell you, Mackey's paper, what they did was they took the outer globular clusters, they took those around the small streams and those which are not associated with any substructure. And they found this rotation, which are very 90 degrees of each other. We tend to think we just don't know. I mean, I didn't say I don't know, but I would like to think that the substructure fell in with the largest galaxy because it brings on its friends. If you bring your friends along, they have small guys, they have streams, and the streams have globular clusters, so etc. So I like to think that one of them component was the biggest merger, and the other one was whatever was there earlier. That's what I interpret.
Thanks.
Another question?
Thank you very much. I really enjoyed the talk. So first, I have a comment on the fact that there are systems with similar mass, and somehow some of them have their disk completely disrupted, and many others no. So from simulation, what we see in this case at TMG is that it strongly depends on all the other parameters of the mergers. Heads-on,
Yes.
versus it totally changed thing. So probably this is what's going on also in the real universe. Then I have a question because I'm not an expert of the result stars. How can you show like an example where you say, no, this is not a halo, this is a tidal feature. How can you distinguish an halo from you said a recent merger?
No, maybe I referred to the disk. Are you referring to this?
No.
The triplet.
No,
This?
this one.
No.
So,
So what I'm saying here is that in this galaxy, I mean, we went too fast. So we have 3 fields, okay? And we find that the halo is very metal poor. It's actually, so what I mean by halo is everything that's not associated with this and that feature. Okay. But eventually they will destroy. Even they will destroy and become part of the halo. That's what I meant to say. So one is a halo would be what is called with no substructure. That's what I meant, with no substructure. So
when it is completely mixed up, you could call that halo or a previous disrupted.
Sometimes I call it adjunctor, sometimes I don't. So I'm not consistent in my terminology. But for us, the question was just to find out what is the counter rotating this, what is the origin? We think, we cannot have sure proof, but we think it's this small SMT gas-rich galaxy.
Thank you. Can I ask also? There are no other questions. Just a curiosity.
It was another. Okay, let's first get the question of the.
So about the last plot, you say that simulation don't show this.
We couldn't find it.
So because of resolution, or they have a different trend?
You are right. Resolution is a problem because some of our galaxies are really small.
Yeah.
But so intuitively, if this from pure lambda CDM. From pure lambda CDM, people expect more number of satellites means bigger halo mass.
Yeah.
Halo mass. Massive halo. So a number of competitors argue that no, what you're seeing is a correlation with halo mass, with the mass of the halo. You're not actually seeing this with the mass of the galaxy which fell in. We have tried looking at it, and we don't know where it is. But if you look at simulations which have very high resolution, I'm talking about the fire solutions. The problem with fire simulations, they have high resolution, but they don't have big sample size. So that's the thing. They have just a scatter problem. So that is, we saw this thing and we were hoping we could see it in simulation, but we don't. That's all.
What about the TMG 50 lustris?
No, TMG 50 doesn't have the resolution of this. Doesn't have the resolution.
And Maria?
Just a curiosity, I'm not expert in the simulation. You said that apparently in the local group there is no correlation between the halo mass and the bulges masses. And looking just behind this plot, which I've not used, is like I would say you have a few points. maybe it's better to wait to the ELT, the Very Large Telescope, and farther away galaxy before having any conclusion, observation and conclusion. And the question I have for you that you do also simulation is,
I don't do simulation.
do you expect a correlation from a theoretical point of view if, for example, you will have an enceladus as a first merge if between the halo mass and the bulges mass?
Yeah.
Do you expect a correlation?
No, I do not. So let me put it this way. We expected a correlation.
You expect.
Because the traditional thing I grew up with and I was studying was that, bulges are caused by mergers. This is what I learned when I was studying. Bulges are caused by mergers. But if you measure the merger mass, the biggest thing is fell in, there is no correlation. We find no correlation.
But who would expect?
I mean, I expect it because that's what I don't know if you know Kennicott, who goes around saying, there are challenge to lambda CDM because there are these thin galaxies without bulges. He publishes a number of papers on these things. So that goes from the idea that everything should have collided and collision should cause bulges. That was the idea, at least, I don't know, at least in Munich, I learned that. So.
Another question from.
Come.
Well, thank you very much. So I want to ask about, so you measured the metallicity of the bulge.
Of the halo.
Of the halo.
Yes.
But can you also measure the metallicity of the disk of the galaxy that you're looking at? And does this bring more information on
the metallicity of the disk, I think, has been measured in many ways. Okay. The disk is always more metal rich. It's always more metal rich, and it has been measured for a few galaxies. So I think M81, the close by where you can resolve it. So you go to the very outer part and where there's no crowding. But then I think many people have done integrated spectroscopy, and they have measured it and they know the metallicity. So the metallicity of the disk could be an in situ process. That's only an in situ process. I mean, see, I would say there are two major processes we are having here. One is mergers and one is secular formation, secular evolution. And secular evolution, does a lot of things. So if we can exclude what is by mergers, then we have to attribute the rest to kind of secular evolution. I would think that the bulge is mainly caused by secular processes. This is what I would conclude from the data, but it's too preliminary.
Comment from Salvatore.
Yeah, no, actually now that a lot of other questions came up about this, so I have a follow-up question. So we currently have a student that is looking at TNG50 to the University of Victoria, and actually we can study mergers around with a mass ratio around 1 to 100. And we are looking at exactly at the bulge formation by mean of mergers of around 10 to 7 stellar masses. And we don't have like a final result. So we know that massive galaxies merger with massive galaxies can form bulges. But we are currently studying what's the impact of minor mergers they are much more frequent. They were, the universe was spraying around the cosmic noon. So we are studying that both for the formation of massive galaxies at high redshift, but also for forming actual and pseudo bulges in the universe. So I think that the resolution of TNG is something good for starting with doing these kind of studies. So yeah.
Okay, I have a last curiosity.
Sure.
So what about the alpha over iron ratio? Could be useful to get, of
Yeah.
course, for nearby system you can do star by stars, but for more distant ones, maybe by integrating light.
Alpha upon Fe is very difficult, So the closest we have tried, which other people have tried, is using DMOS on the Keck telescope to do it for M31 with low resolution, medium resolution spectra. But there is, you told me about the ERS JWST program to measure for M31. So if that is successful, then we can use it for other galaxies. But
for other galaxies, you may want to use the integrated light spectroscopy because you will not use. You get a question? No. Okay.
Yeah. So it is to come, but it is very difficult.
Yeah. Okay. I think there are no questions from the public at home. I think we are running a bit late, so let's thank again Richard. You next.
So
Very interesting, Richard. Probably we needed 1 hour. You need was more suited probably for a Jack 1 hour duration because many things. Very interesting. You,
I left, yes.
my back. Stop the recording.
Eduardo, ciao, come stai? Va bene con me? Ah, bene.
Abbiamo parlato un po' della fantastico.